So, hi everyone, thanks for coming in. Thank you, Robert, for coming in to present this talk for us. And Robert is a PhD candidate at ITSIA. He's been working a lot on generalization in neural networks, and now he's going to present some of his works to us. And I'm very interested to hear about them. So thank you, and let's hear your work.
Yeah, thank you for the invitation. And I will talk to you today about how principles from compositionality can improve systematic generalization of neural networks. This is a joint, like these works are joint works with Katsuki Irie, Csordás and Jürgen Schmidt-Huber. So first about the motivation. Despite the great recent process in machine learning, there are still some issues which seem to be very trivial for humans, but very non-trivial for neural networks. For example, this is an example from Gopher, which is a large language model for DeepMind. And in the beginning, it starts by discussing physics with the user, and it seems to know a lot about physics, and it is very knowledgeable and makes reasonable answers. But then in the end, the user asks, what is 15 times 7? And the model just answers 5. Which is obviously wrong, and it is like not just a bit wrong, but completely off. And we don't really have understandings why the model make these kind of issues, and what is the underlying reason of this kind of not being able to generalize despite of seeing nearly infinite data in terms of human, like humans see much less data than the whole internet, and they are still able to learn these things, but the models cannot. This is a bit outdated example at this point, but like also for image captioning, there are some famous mistakes that the networks can make, and all of these mistakes are pointing towards the direction of the networks not learning generally applicable rules, but instead of that, learning some kind of trivial pattern matching. This is another example from DALL-E 2, which is a pretty new thing. And here the user specifies a specific arrangement of geometric objects with specific colors. And the network completely misses to fulfill the specification, but just produces some kind of shapes with some kind of colors. In theory, Imogen from Google improved this, but I have not seen similar queries. But people say so. So it is impossible to know until these models are open. So my goal would be to make models learn generally applicable rules or programs instead of just purely matching patterns. And if the generalization is about generalizing to a different problem than the model was trained on, but this different problem is governed by the same rules as the training, then we talk about systematic generalization. And for example, one of the most favorite, most well-known papers in the field, Blake and Baroni say that if we learn to use a new word, then immediately, as we know the meaning of that word, we can use it with the other words which we already know. And this is like some kind of algorithmic recombination with the already known knowledge, which is currently not working well with neural networks. So as I said, systematic generalization is about using our knowledge in novel ways on novel combinations of rules. And there are several subtypes of this. For example, systematicity is roughly about combination of well-known constituents in novel ways. And productivity is, roughly speaking, generalization to longer sequences. And I think that this is probably one of the major obstacles towards general AI, because it prevents models to work outside of their very specific training regime. First, how do we measure systematic generalization? And usually we do this by using some kind of systematic datasets, synthetic datasets that are generated in a way that there is a systematic split. So the training set is in some way easier than the test set, or it is just like different combinations. In that case, it's not necessarily easier, but it's just different. It is also possible to do this with real-world data if we have some kind of heuristics to measure the complexity of the data and then split it by that to training and test set. And there are some standard datasets that are typically used. For example, SCAN, which is about translating high-level command sequences into low-level command sequences. Then there is CFQ, which is about semantic parsing. PCFG, which is similar to SCAN, but more complex, and it operates on lists of operands, and it has more complex operations than SCAN. Then there is COX, which is again about semantic parsing. And finally, there is also the mathematics dataset from DeepMind, which is about solving high school math problems. And it's not directly about generalization, but since it comes with a difficulty-based split, it can be actually repurposed to measure generalization. So about existing methods, neural networks are preferable because they are very flexible and they can learn to perform all kinds of tasks without any engineering or minimal engineering. But the problem is that they don't generalize well. And the goal of my work would be to enable them to generalize better. Then there are some meta-learning based approaches, which are underexplored, but there are some works out there. But it's unclear why they would improve systematic generalization in general. And then finally, there are the neurosymbolic methods which work well, but they require some task-specific engineering. Let's say in case of semantic parsing, what people typically do is to do the parsing by a neural network and then generate the sequence by some kind of hard-coded program. So why is this problem so difficult and what is missing? The main problem with generalization is that there is no optimization pressure at all to generalize. That's by definition. So for the optimization process, it doesn't matter whether the model just memorized the whole training set or actually learn some generally applicable rules. And because of this, probably our best hope is to use some kind of inductive biases. But then the question is, what are those biases? And we think that the basis of generalization should be compositionality. So the problem should be decomposed to elementary constituents. And these elementary constituents should be reused to recombine in novel ways in order to solve the novel instances of the same problems. For example, here, there are three examples about adding and multiplying and how the network should learn a plus b times c. And we would prefer it to learn an adder and the multiplier separately, or like in some way separately, and not a fused module for adding and multiplying together, because then if you want to, let's say, add three numbers or do anything else which consists of the same operations, it will just not work. A slightly less trivial case of which is not preferable is what if the network learns the same operation multiple times? This can be this is bad, obviously, but not necessarily fatal. But for example, one of the downsides is that it requires much more data because it has to learn the same instances multiple times. And it also receives, let's say that one of these operations receives a smaller range of data. Let's say one learns to multiply in range of 1 to 10, the other learns to multiply from 1 to 100. Then the one that received the training data from 1 to 10 is not necessarily generalized to the full range, while in the other case, it would have much more chance to learn to generalize even outside of this case, but at least it would work from 1 to 100 for sure, because it is the other instance is trained in that range. It also means that if novel combinations requires a novel element operation to perform the same underlying operation, that would mean that for instances that are not seen during the training, you would not have the new module that performs that operation, and then it would not work, most probably. So compositional computation is also tightly tied to sequential computation. So in order to be compositional, you want, instead of a short parallel computation, you want a long and sequential computation. And this is because you have to have the result of the previous operation ready in order to be able to process by the next operation. And this is in contrast to what we typically do, especially with transformers, where we typically have a relatively few number of layers. which are processed in parallel. And that means that, like, say that if you want to add 4 numbers, then you will most probably learn one piece of 4th-way adder instead of learning a 2-way adder, which is applied 3 times in order to add 4 numbers. And then, of course, if you would want to add 5 numbers, then it would not work. So first, let me start by analyzing whether the current neural networks learn something which is kind of reusable modules implicitly. Of course, they don't have this structure explicitly, but they might have learned it somehow in their weight space. So in the literature, there are many works that are concerned about whether there is some modular structure in the neural networks, but they never connect that to the actual functionality performed. They show that there are clusters, but whether these clusters are something meaningful, that is unclear. And our goal in this work was to specifically connect these clusters to the function that the cluster performs. And we do that by first pre-training a neural network on we call it full task. Like, these tasks are designed to have some kind of different aspects to it. So we can select one aspect and we define the task based on those aspects. Here in this example, we learn to add and multiply numbers. And after the neural network is trained, we freeze its weights. And after the weights are frozen, we select a subset of the dataset as a subtask. And we train binary but differentiable masks for all the weights in the neural network, which reveals the connectivity pattern needed to perform this task. This will remove all the weights that are not needed for this task. For example, those might be or might not be needed for the other task, but it highlights the weights that are necessary for this particular one. If we do this for all of the subtasks, then we can see for each weight which is the set of the tasks that it is required for. And we can then have shared weights or task exclusive weights, which are exclusive to one or the other task. This can work with arbitrary number of tasks, but for simplicity, we usually just consider 2. So the method itself is very simple. It is just a Gumbel sigmoid, which is basically Gumbel softmax just with one output. And we also have a regularization term that makes the mask be 0 in case the weight is not used. So then the question, whether the networks are modular, let's see. So we design a diagnostic task to test that. And particularly our intuition behind this is that in practice, you would not know which kind of modules there are in the network, but there would be some state which contains all the information that is known by the network. In case of RNNs, this is obviously true. And if there is some modular structure, then that modular structure should focus on some piece of that hidden state and extract information on those, and then perform some operation and then write back the information to that. In order to simulate this, we always feed the neural network just with one input, where all the states that we produce are concatenated together. So let's say that in this particular task, the task is to add or multiply, as in the previous example was. And we present both the input numbers and the operation selection as one vector. The input numbers are here represented as a, first of all, these are numbers in range of 1 to 100, and they are represented by digits. So it's like, and they're 1 hot. So for one number is then 2 1 vectors of 10 elements. So one number is 20 elements. And here are 2 numbers, so 40 elements plus the operation selection, which is just 1 hot, and so it is 42 elements. Just to have just to be able to imagine how it looks like. So in this case, we would expect something that the inputs and outputs are shared because they are presented at the same vector, and then the hidden states are specialized to addition and multiplication. That would be the ideal case. If we measure what actually happens by measuring the overlap between the weight masks, then we can see that there is a significant amount of specialization, but there is also some overlap. So first about the metrics. intersection over union is one of the metrics that we measure. And obviously, if this is high, then there is an overlap between them. But the problem with the intersection over union is that if one operation is the subset of the other, let's say that addition is needed to perform multiplication, and the multiplication needs also more things, then it would mean that the intersection over union is low, even though one is the subset of one mask is the subset of the other. In order to measure this more properly, we also introduced the so-called intersection over minimum, which measures basically the subsetness, how much one of the set of the weights is subset of the other. And we can still see that even that metric is reasonably low in the hidden layers of the neural network. It is below 0.5, it is like 0.34 roughly, which is not ideal, but it means that there is some specialization happening. We also measured how the performance of the network breaks down if we remove task-exclusive weights. And we do that by training the masks on one of the operations, removing the weights that correspond to that operation, and then measuring the performance with the rest of the weights. And it turns out that feed-forward networks and recurrent neural networks have a different behavior here. And feed-forward networks usually break down by just ignoring the operation selection and performing the operation that was not removed from the network, like the one that is not corresponding to the mask that we removed. While in the LSTM case, the network usually tend to produce just invalid results. So another more interesting question is whether the same module is used if the functions are identical. In order to test that, we present the network 4 numbers, and we require from the network to add those numbers pairwise. Of course, if it is a feed-forward network, then we just present one of these pairs at a time and we zero out the other, because otherwise there would be always a conflict in the activations, and it is not possible to represent the 2 different numbers in the same activations. So it would not be possible to share, but we prevent that by just feeding one and requiring one result at a time. And in this case, ideally, what would we expect is that the inputs and outputs are not shared, but then the hidden layers are shared because the underlying operation is the same. And learning the identity mapping, or like the same mapping between the 2 inputs, is probably easier than relearning the whole function all over the place. But we found that this is not true. So the sharing is very low, way lower than the previous case where we would not expect sharing actually. And this means that practically the 2 subset of weights that perform the 2 operations are completely separate. And in order to test this theory whether they are completely separate, because there are still some overlap, we did another experiment where we actually invert the masks. So we take the masks that perform well with operation, with operation 1, we invert those, and then it turns out that it will perform well on operation 2, but not on operation 1, which means that they are actually exclusive. We can do this with both masks, and it turns out that the complementary masks work for the complementary tasks. So they are indeed completely separate. That means that—
Could you clarify here? You have a mask, the tasks, effectively you have 4 numbers.
Yes.
You do addition on the first 2 and addition on the second 2.
Yes. So So I train first I train the masks. I train the network to learn to know to do both of these additions. When it knows to do that, I freeze the weights. Mm-hmm. Then I just take one.
Feed-forward network.
It is done with both. It is okay. Yeah, and the result is the same. But let's assume that it is a feed-forward network. And yeah, so then I take just one of the pairs. So I always zero out the other 2 and train the mask on that. That removes all the weights that are needed for the second pair, but are not needed for the first, right? Mm-hmm. So now if I test both pairs, then it turns out that the first will work because the mask was trained for that. And the second will not work because that is removed by, because it is not needed for the first operation. Mm-hmm. But then if I take this mask and I invert it, mm-hmm. then it will break the first operation, but the second operation will work.
That's
so now,
interesting because, what's interesting to me is there are probably some units that are not relevant to either task.
Yes.
And when you invert it, then you sort of add them back in.
Yes, but those were back in when there was no mask as well. So they don't hurt performance by themselves. It's just a way. You could also do or together the two and use that as a mask to remove the unneeded ones, but it was simpler like this, and it still showed that they are like basically independent. So
cool.
So in order to test this in a more complex setting, we also try to do continual learning on permitted MNIST. But because this, like in permitted MNIST, each task is defined by a different permutation of MNIST digits. But since it is a permutation, there is no spatial structure anymore, so it doesn't make sense to use COMNETs, so we use MLPs. But note here that only the inputs are permuted. That means that for the MLP, all the layers except the first one could be reused. They are exactly the same transformation, just you have to permute the weights of the first layer in the same way as the input is permuted, basically. And then this transformation to move from one task to the other is undone, and everything could be reused. So in order to be able to do this continual learning, we modified our method a bit. So first of all, the weights and the masks are trained together in this case, and we train on task one that reveals the connectivity, and we have the weights. We freeze those weights, and we reinitialize the rest of the weights. There is one exception here. We always reinitialize the first layer. And that is because there is a different permutation. It might happen that the same weight would now have to be used for a different purpose than it was in the previous task. And because that is frozen, it could not be used anymore. So in order to prevent that, we just reinitialize the whole thing. So we are not able, at the end, we are not able to perform all the tasks, but we are able to give an upper limit on how much sharing is possible if this is not a problem. So we do this for second task and for third task, and then we have a set of tasks for each weight. And we can measure the overlap between the weights for the different tasks. And this is the result. Here, the different colored bars are the amount of sharing for after different number of tasks learned. And it turns out that even after 10 tasks learned, there is basically very few sharing in the hidden layers. There is some in the last layer, but if you investigate the actual weight masks, it turns out that this layer saturates pretty quickly because it's pretty small compared to the others. And then the network is just forced to reuse the weights because there is no enough weights to be to learn a new set of them. So unless there is a explicit force by limiting the capacity, there's still no weight sharing in the hidden layers. This confirms our previous findings. So to summarize, there is some amount of specialization between functions, but there is no reuse for identical functions. Now the question is what does it mean for generalization? And we investigated SCAN, and specifically, we were interested in distinguishing between two problems, two hypotheses. One of the hypotheses is that when we are considering a split which is designed for testing generalization, then there is no enough information in the training set of that split in order to learn how to actually use those tokens properly, or those constructions that are failing then in the training. While the other hypothesis is that, but in this first hypothesis, the rest which works is actually learn the proper algorithm to perform the task. Just it could not learn that algorithm because there is no enough data in the training set for the generalization split. But the other hypothesis is that it is just not learning a general algorithm. And how can we distinguish between this? We train the network on the IID data on SCAN. That network will perform perfectly on all the generalization splits, which means that it knows to perform those operations. So now we can rule out the case that it doesn't have enough information to learn to perform those operations because it we know that it actually performs them. When then we freeze the weights and we train the masks on the specific generalizations, the training set for the generalization splits. And it turns out that if we do this, then it breaks the performance on the test split for the test set of the generalization split. And this should not be the case because all the rules underlying all the sets are the same. So if this is the case, that means that there are some weights which are exclusive to specific combinations that are just in the test set for the generalization split. But there are no such rules that are exclusive for the test set of the generalization split. So then it must be that the patterns learned are not actually corresponding to an algorithm, which is general for all of these tasks, but it must be some kind of example-specific combinations. And this is not good. And of course, like here for a new split, you will not have those weights. So it is impossible to perform a new kind of composition. And we confirm this for transformers and the LSTMs, and also on mathematics dataset is the same basically. So this means that the modularity exposed by these neural networks is not supporting compositional behavior, which is again not good. But then why is this the case for transformers? Transformers specifically seem to have a nice structure, or at least a better structure than like fit-for networks and RNNs. At least like for reusing the weights, the same weights are replicated over all token positions. So that could be technically, it could not mitigate completely the issue, but at least it could improve it a bit. And also the structure, if you think about the layers of the transformers and how they are laid out on the tokens, it reminds us, or it could remind us of a computational graph. We can draw a computational graph in the layers of the transformers, at least for arithmetic tasks, and those should generalize pretty well. Like there is no component in them what should be specific to, let's say, certain length or certain combination. But we still see that they don't. So the question is why? And yeah, so we think that one of the main issues is that there is typically no layer sharing used in these transformers. So if you assume that this kind of construction of computational graph happens in the layers, then you want shared layers because you want all the operations to be available in all layers, because that defines in which order they could be executed. And you want them to be executed in any order, so you would want shared layers. So this is one hypothesis, we should use shared layers. The other hypothesis is that most of the transformers use absolute positional encodings, which is again not general, because we are interested just in offsets or nearby operations and not really on the absolute positions. So the simplest model that satisfies this hypothesis is that is a shared layer transformer with relative positional encodings. This shared layer transformer is not the universal transformer actually, but it is a simpler version which doesn't have ACT and it doesn't have layer encodings and things like that, but it doesn't really matter. So we'll investigate that in the following, and we'll also discuss some of the methodological problems with what we found in published papers. But first, a case study. So there is this problem called the end of sequence decision problem, and it's a paper with Newman et al. From 2020, and it examines whether the issue with the scan generalization is that the network actually don't know to produce the correct output, or it just overfits to a certain length and it produces the end of sequence token in the wrong position, but otherwise would know to continue the sequence correctly. And how can they test this is that they remove the end of sequence token from the output, from the softmax output of the network. They fill it minus infinity before the softmax basically. And then you can take as many characters as the ground truth output and compare those. And it turns out that if you do this, they call this oracle evaluation, then this improves the performance a lot, which means that in most of the cases, the end of sequence token is produced in the wrong place, but otherwise the network knows something about continuing the sequence. But even more interestingly, if you train without ever producing the end of sequence token, then the performance improves further. So in this table, you can see the performance of their networks and our networks for different length cutoffs. For the length cutoff is the length at which the maximum length, which is still in the training set, and from what the test set starts in the length generalization split in scan. And length cutoff of 26 is especially interesting because there are some ambiguities below length cutoff of 26. Anyways, the upper part shows the results from the original paper. And you can see here that the standard evaluation with end of sequence token is basically giving 0 performance, while with Oracle length evaluation, it improves a lot, but it's still not 100%, or it is, but only from very long sentences. In contrast, in our case, which is the bottom of the table, we always evaluate with end of sequence token as usually done. And we use one more layer. We found that also critical, but that will connect to the later part of the talk, so bear with me with that. And you can see that even though that one more layer is added, it improves from 0 to, let's say, 30% in some of the splits, but that's still far from perfect generalization. But if we use relative position encodings, then suddenly it starts generalizing pretty well from length cutoff of 27. While if we also use shared layers, then it already generalizes from 26, which is the length that it becomes not ambiguous. So this means that basically the end of sequence problem, the end of sequence token problem is solved, at least in this case. So it looks promising. But let's see what other issues exist in the literature. So first is that IID validation set doesn't tell us much about the generalization. And it is a common practice to use IID validation set for model selection and for hyperparameter tuning. Even worse, they are sometimes used for early stopping. In this table, you can see with the numbers outside of the parentheses, the IID performance of different models, while in the parentheses, you see the OD performance on the specific dataset. And you can see that almost for all of the cases, the IID performance is 100% for all of the models, while the generalization performance can vary wildly from for example, for scan, some of the models is 20%, while the other is 100. So, and still they are both 100% on IID. So if early stopping is used on the IID dataset, then we can result in a situation which, for example, Cogg's dataset was. So just by disabling the early stopping in their dataset and running it a fixed number of iterations, brings the performance from 35% to 65% without doing anything else. And also that 35%, if you change the seed, it could fall immediately to 2 or 0%, basically, you can get anything. While if you just disable early stopping, it is pretty robustly converging to 65. So motivated by this, we did an experiment where we measured the generalization performance periodically for 3 different models. Let's not worry about what those models are actually, but they are just showing that how different models behave. And we plot the generalization performance, and with the vertical lines, we show where the model's training would stop if we would stop on the IID validation set. And this shows that the model's performance is nowhere near the end performance, while the early stopping would stop it on the IID data. Even worse, we found some cases where the loss can be positively correlated with the accuracy. And initially this sounds like a bug, but it is not. So this is the validation loss versus the test accuracy, but you can see also this in the test loss and test accuracy. And this is a different data set, by the way, and it holds between data sets as well. And in order to figure out what is happening, we decompose the total test loss into 2 components. So we measure the accuracy periodically over training, and we mark each example as good or bad. And so if ever during the training, the output of the network was correct for that specific example, then we mark it as a good example. Otherwise, we mark it as a bad example. If we do this, then we can decompose the total loss of the network to the loss of the good examples and the loss of the bad examples. And it turns out that the loss of the good examples quickly shrink to basically zero, while the loss of the bad examples goes up much more than the good ones shrink. So they dominate the total loss, and total loss will grow. And this is usually a much smaller subset of the dataset, let's say 10% of the examples or something, but it still can dominate the total loss. And yeah, this is basically just overfitting to a subset of the total examples in the dataset. And yeah, so this is another reason why not to use the loss, but if you want to use, then use the accuracy for validation and early stopping as well, especially. Even if you don't see this behavior, then still like tuning on the loss is dangerous. For example, in this case, you can see that the network exhibits a epoch-wise double descent phenomenon. So accuracy grows monotonically, while the loss goes down, then with up, then down again. So how can we fix these issues? So first, I think that we would need an OOD validation set. And this is tricky because then how do you define what is OOD and IID? And basically, I would say that we need different difficulties of splits. And then we train on the easy one, we validate on the medium one, and then we test on the hard one. So this then still requires learning the correct algorithm because the final test is harder than everything that you've seen before. But there is some indication in the training and that indicates what we expect from the model. For some kind of generalization, this is easy. For example, for length generalization, you can just divide by lengths, short ones to training, middle ones for validation, long ones for testing. But for the other problems, it is more difficult to come up with these kinds of splits. And maybe we should use an ensemble of data sets, or like more research is needed to figure out what can be done there actually. So how far can we get with this? Actually, pretty far. So this is the different versions of our models on different datasets. The right column shows the previously reported performance. So okay, scan is a pretty toy example, but even on CFQ output length, it improves generalization from 66 to 81%, or for COX from 5% to 81%, and so on and so on. So it is a reasonable improvement compared to how simple it is. And another notable thing here is that relative positional encodings with universal transformer is almost in all the cases the best model, but if it is not, then it is tightly, like it's very tight compared to the best model. But the problem is that if we now test this model on synthetic datasets designed to test length generalization, then we find that they are still not working well. And the question is, what is still missing? So let me first introduce the testbed for what will follow. This is the so-called compositional lookup table task, and it consists of 8 symbols, for some reason defined by 3-bit binary strings, but they are 1 token. So all the 3 bits are 1 token. And there are also functions that are applied to these symbols. And these functions are always unary. So they take 1 argument and they are bijective. So you cannot result in like losing some symbols after some function applications. So this task is to apply a series of functions to an argument. Very simple. These functions are generated randomly, but are fixed during training, of course. And then the task is to generalize to longer sequences of function applications. And this can be also used in 2 ways, actually, to demonstrate the failures of the current models. One is that they don't generalize to longer sequences, but we also found that they can be sensitive to the order which the sequence is presented. So it might happen that it is generalizing from left to right, but it's not generalizing from right to left. Of course, the generalization is always measured in the same order as training, because it means that this network is sensitive to how do you train it. And this should not be the case, because in general, we don't know which should be the order. but probably it should not be left to right nor right to left, but in more complex cases, it is some parse tree or something, and the network should dynamically decide where to start actually processing the sequence. So one of the hypotheses is that actually in the current literature, the transformers used are very shallow. For example, there was the example from the previous table where we said that we added one more layer in order to make it work. So that was a 2-layer transformer in the original paper. So if we assume that this corresponds to some kind of computational graph, that means that the number of layers determines how deep of the computational graph can be before the operations should start fusing into one operation in one layer. So that means that we need to use many shared layers. Not only that, but most of the computation should be sparse. So if we are processing a computation graph, then only the nodes that should be updated are the ones that receive some new input. So let's say that here, while processing the multiplication, the addition should be kept fixed because the multiplication has the priority. It should produce the result first, and then the rest should take over. But until that point, the columns should be unchanged for those tokens. And this turns out to be pretty hard in transformers because they have layer normalization, they have residual connection. Okay, the residual connection is not that hard maybe to overcome, but the layer norm is for sure, especially if repeatedly applied. So we decided to add the mechanism to enable to keep the columns unchanged easily. And this we call copy gate. And it skips the whole transformer layer. So we start by like as usual, we have a multi-head attention, layer norm, residual connection, and so on. The only difference is that we don't have a residual connection in the data part, in the after the feed-forward layer. Actually, later after the publication of the paper, we found that doesn't really matter. So you might also just start with a normal transformer. But then we also have a parallel branch to the feed-forward part. So you have a attention, then it branches to 2 parts: feed-forward part for the data, and then feed-forward part for the gate. And this is usually a much smaller feed-forward network than the data part actually. And this has a sigmoid function applied to it. So it rescales the activation between 0 and 1. So it acts like a gate. And then we can combine the outputs from the layer norm, like the outputs from the data transformation and the input before the start of the transformer layer. So if the gates are closed, then the whole transformer layer is skipped. This also enables initializing these gates to be closed, so the transformation to be skipped. And this biases the network towards sparse computation. So does this help? It turns out that it does, but only partially. So if we check the performance of the transformers and the transformers with relative position encodings, then it turns out that they work very badly on the CTL task for longer sequences. But then if you add only this gating and you add more layers, then it immediately starts working almost perfectly in one of the directions, but it doesn't work in the opposite direction. So this is not good because then in general, you don't know the direction. And the question is, what is still wrong? So by examining the attention patterns of the transformer, it turns out that absolute position encodings overfit to the positions seen during the training. Relative positional encodings, on the other hand, overfit to the offsets seen during the training. So note here that the result of the whole computation is read from the last column of the transformer. This is like a sequence classification model, so it is always from the last column. But if the task is presented from right to left manner, then always the second column will contain the result of the last transformation. That means that the offset between the last column and the second column will be longer if the sequence is longer. And it turns out that relative position encoding really doesn't like to do this. So it overfits to the offset range that is seen during the training. So, but actually, do we care about offsets? I argue that in most of the cases we don't really. So what we care about is to find some matches which are the closest to the current column, and we don't really care about the exact offset that they are. Maybe we care about some properties, but not the offset. And so in order to do this, we introduce the so-called geometric attention, and this is an attention which is biased towards the nearest match. So it doesn't care about positions nor offsets. It just cares about finding the source position which is closest to the target position, and it has a good match. And this is inspired by the geometric distribution, and you will see later why. But in order to do this, we should first define the order or the preference ordering of the attention. So let's say that we have a query position here in the token position A. Then we radiate outwards from this position, and we say that the network prefers the match that is closest to this position. So first it looks at the right side, then if there is no good match there, then it looks to the left side, then it looks further to the right, then it looks further to the left. So in the right side in this matrix, you see like for a 5-line sequence for all source position, all target positions, which source position is preferred. And this just defines an ordering. So if we have this ordering, then we can do the following. So we produce keys, queries, and values as usual. But instead of applying a softmax function to it, we apply a sigmoid. This produces scores between 0 and 1 for each position. We can interpret those as the probability of wanting to attend to that specific position. Now we can construct the final attention score by multiplying the probability of attending to that specific position by the probability of not attending to any of the previous positions. And here is where the ordering comes in. And this kind of looks like the geometric distribution. And interestingly, it is possible to do this efficiently by doing a cumulative sum in log space and then just scalar subtracting the correct offsets from each other. So in addition to that, the only position information the network has is that it can focus on its left or right side. This is done by adding a bias that is dependent on which side the network prefers. If we do this, then we get the neural data router architecture. The 4 key ingredients are the copy gate, geometric attention, and many shared layers. And there is no relative nor absolute position encodings used. So an alternative view on this is that it is an architecture which has a much simplified control flow. Each of the tokens, basically tokens, yes, processing units can look at its local neighborhood. Based on its local neighborhood, decide what to do, and then process the whole transformation locally. And this intuitively should not really depend on the length of the sequence. It somewhat depends on the depth of the computational graph, but only by like if there is some degradation of the symbol quality over the transformations, that might still be a problem, but it's still much reduced than in the normal case. And it turns out that if we do this, then we have 100% generalization to longer sequences on the CTL dataset. You can see that all of the other versions are bad, except we have a diagnostic version here, which performs almost perfectly. But that is specifically constructed to test our hypothesis about the problem being overfitting to a specific offset, and it is not generalizing to other datasets, as you will see on the next slide. So we tested this also on simple arithmetics examples, which is like just modulo 10 arithmetics, but the length of the parse tree can grow bigger. And there is also a well-known dataset called ListOps, which is just operation defines on lists. And then these operations can be embedded into each other. And we actually made this more difficult by not just having longer lists of arguments, but also deeper compositions. And we make sure that those compositions actually are considered in the result, because normally it can happen that because many of these operations are selections like median or maximum or minimum, it can be that you can just ignore half of the arguments and just pick from those which are available if you cannot consider after certain depth, and you will still have a reasonable heuristics that performs reasonably, let's say 70% or 80%. And we balance it such that this is not possible. So if you do that, you can still see that our NDR architecture generalizes well in these cases, while the others don't really. So we also analyzed the attention maps of the transformers. This is iterative position encodings, and it is trained up to 5 steps, which means that from t equals 5, it is out of distribution here. And it turns out that the attention map becomes blurry after the number of steps it was trained for, if the sequence length is longer, and then it fails to attend correctly to the correct positions in order to perform the longer sequence of operations. While if you look at the attention map of the NDR, then it stays sharp around the area of interest. Of course, like it is not focusing in each step for each of the operations, but at the point where the actual operation happens, it stays sharp, and like it fades away the one that is already processed. Yes?
When you say steps, do you mean the number of repetitions of the layers?
Yes. So here, yes, here it's basically RNN in the universal transformer is just an RNN in the, not the input dimension, but an orthogonal dimension, which is the depth.
So it's decided for each input how many times it will be repeated and trained.
It is a fixed number, but yes, and it is trained, like it depends actually. So we also do tricks like training with less, for some dataset, training with less layers than testing for, because it just speeds up training. But you can just stick with the largest number that you know that you have, and it will still work. So if you do it more iterations, it doesn't matter, it stays stable.
I'm really fascinated by what would happen if you would change the number of layers in training respectively to the length of the input, for example, and then suddenly see what happens on the longer input.
So you can do that if you want, but then you are using information about the length which you don't want to. We also had experiments with adaptive computational time, which works to some extent, but it was not, it worked actually. So it can decide adaptively. But yeah, like for example, for ListOps, we know that the maximum depth of computation is like, I don't know, a certain number during the training, I don't remember how much. We set the number of layers a bit more than that in order to have also time to, like, if it wants to gather some global information, and also the readout takes one more extra step because it has to copy to the last column where the result is read from. And but this is obviously not performing well for the test set, which is much deeper. And then we just increase the number of layers during the testing, and done, it works. So yeah, this is about the attention map. Do you have any other questions? No? Okay.
Not yet. So
we also examined the gates, and it turns out that it works as we expected. So this is the CTL task, and it has to apply this sequence of functions to the argument. And only, of course, in the first step, it can only apply the first function because the rest don't have the inputs ready yet. And you can see here that the rest of the columns just stay closed gate, and then the only column that updates is the first function is applied. Then they, as soon as the argument becomes available for the rest of the columns, the gates of those columns also open and they perform their computation. Another thing that we tried is we tried to measure how much this intuition about having a computational graph and each layer performing one operation, or at least data operations that don't have data dependencies, how much does this hold? And what we did here is that we took the CTL with 10 function applications and then tried a different number of layers. And note here that for 10 function applications, you actually need 11 steps at least, because you have to read out the final result. For each function application, 1 step plus reading out the final result. So if we do this, then you can see that as soon as the number of layers fall below the theoretical limit, which is 11, then the test performance breaks down, while above that, it is 100%. And interestingly, the IID performance it is still good long after that, because it can still fuse the operations together and perform them with much fewer layers. But then, of course, that will not generalize. So this supports this way of thinking about transformers as building a computational graph and computing the result on that. Okay, I just explained this already. So to conclude, then we would prefer neural networks everywhere because they are flexible and then they can learn anything basically. But unfortunately, they have poor generalization properties. So improving those would be very advantageous. And we think that compositionality should be the basis of generalization. We should watch out what kind of baselines we use and what methodology we use to train those. And finally, if we want an architecture that generalizes in case of these arithmetic style problems, then we want to use a transformer with many shared layers and possibly with gating and the geometric attention, which removes the dependence on absolute and relative positions. And thank you. And I'm ready for your questions.
Thank you. That was great. I'm going to stop the recording so that we can be more informal.